The reef announces the presence of the Napoleon fish before it fully comes into view. Water shifts. Smaller fish scatter in widening arcs, not in panic, but in recognition. This is not a fast hunter, not a sudden strike predator. It moves with mass and confidence, a shape so large and deliberate that the ecosystem adjusts around it as if around a passing tide. Its body is thick, armored in heavy scales that catch the light unevenly, its head swollen into the distinctive hump that gives the species its other name. The humphead wrasse does not blend in. It does not need to. Coral reefs are often imagined as fragile, delicate structures, easily broken by storms or warming seas. But from the inside, they are places of constant pressure. Every surface is contested. Every organism is either growing, defending, consuming, or being consumed. Coral itself is alive, a colony of tiny animals building limestone skeletons over centuries, only to have those structures gnawed, drilled, and grazed by an army of specialized feeders. Among the most destructive of these are coral-eating starfish, slow-moving but relentless, capable of stripping reefs down to bare skeleton with shocking efficiency when their numbers explode. Against such threats, speed and stealth are not always the answer. Sometimes the reef needs force. The Napoleon fish is built for force. Its jaws are massive, reinforced by thick bones and powered by muscles that dominate its head profile. Unlike fish that snap at soft prey or filter plankton from the water, this animal bites down on problems most others avoid. Hard shells, spines, armor. Its mouth closes not with a quick nip, but with a crushing pressure that echoes faintly underwater. This ability opens a menu unavailable to most reef fish, allowing it to consume sea urchins, hard-shelled mollusks, and, critically, crown-of-thorns starfish in certain regions. Crown-of-thorns starfish are not villains by nature. They are native to many Indo-Pacific reefs and play a role in maintaining coral diversity by preying on fast-growing species. But when conditions favor their reproduction, often due to nutrient runoff or the loss of predators, their populations can surge. A single individual can consume vast areas of living coral, everting its stomach onto the reef surface and digesting tissue externally. Multiply that behavior across thousands of starfish, and a reef can be reduced to a graveyard in a matter of months. Recovery from such events can take decades, if it happens at all. Here, the Napoleon fish enters the picture not as a savior in a dramatic sense, but as a regulator. It does not hunt starfish exclusively. It does not patrol reefs with intent. But when it encounters one, especially a smaller individual or a vulnerable section, it can bite through spines that deter nearly every other predator. The starfish's chemical defenses and sharp projections are insufficient against sheer mechanical power. Each starfish removed is one less mouth-dissolving coral tissue, one less slow-motion demolition underway. The effect of this predation is not immediate or obvious. Coral does not rebound overnight. But over time, in reefs where large wrasse populations persist, starfish outbreaks tend to be less severe. Coral cover stabilizes. Structural complexity remains intact. The reef retains its vertical architecture, which supports fish diversity, nutrient cycling, and resilience against storms. The Napoleon fish does not repair coral directly. It removes pressure. It creates space for recovery by eliminating a major source of damage. This role is only possible because of the fish's physiology and life history. The humphead wrasse grows slowly, reaching maturity late compared to many reef fish. It can live for decades, accumulating size and influence over time. That slow growth makes it vulnerable to overfishing, as populations cannot rebound quickly once depleted. Yet that same longevity means that an individual fish, once established, exerts its ecological role year after year, stabilizing conditions through consistency rather than intensity. Its behavior reinforces this stability. The Napoleon fish maintains large home ranges, cruising familiar sections of reef repeatedly. It is not territorial in the aggressive sense, but its presence alone alters the behavior of other organisms. Smaller fish give it space. Invertebrates retreat deeper into crevices. The reef reorganizes subtly around its movements. much like a city adjusts to the regular passage of heavy machinery. Nothing dramatic, just accommodation. There is a quiet irony in how such an imposing animal operates. Its intelligence is evident in its awareness and curiosity. Divers often report that individual wrasse recognize them, approaching slowly, inspecting with one eye, then circling back. This cognitive complexity suggests a sensory world richer than that of many fish, one capable of learning and memory. Yet its ecological impact is not driven by clever tactics or social coordination. It is driven by jaws, by the simple ability to apply enough force to consume what others cannot. That simplicity matters. Reef ecosystems are often discussed in terms of intricate relationships and delicate balances, and rightly so. But not every solution within those systems is subtle. Some problems require removal, not negotiation. When coral-eating starfish proliferate beyond control, no amount of mutualism or competition can slow them. They must be eaten. The Napoleon fish is one of the few animals capable of doing so at scale. The loss of these fish from many reefs has been instructive, if deeply unfortunate. In regions where humphead wrasse have been heavily fished, starfish outbreaks have tended to be more severe and more persistent. Human intervention, through manual removal of starfish, has attempted to fill the gap, divers injecting toxins one by one in labor-intensive efforts. These actions underscore the role that was once played effortlessly by a living animal moving through its environment as it evolved to do. From a distance, the Napoleon fish can seem almost out of place, too large, too slow, too conspicuous for a reef full of fast-moving specialists. But that perception misses the point. Its size is the feature. Its visibility is the signal. It is not there to chase. It is there to impose limits, to remind certain species that the reef is not an open buffet. As it moves along the coral slope, passing massive heads and branching structures, its presence represents accumulated time. Time spent growing. Time spent feeding. Time spent exerting pressure on a system that depends on pressure being applied in the right places. Without such animals, reefs do not simply lose color or diversity. They lose enforcement. Grazers overgraze. Corallivores overconsume. The balance shifts toward degradation. There is no malice in this process. It is not a moral failing of starfish or urchins or any other organism. It is a mechanical outcome of missing components. Ecosystems are machines built from flesh, bone, and behavior. Remove a critical gear and the system still runs, but poorly, grinding itself down over time. Watching a Napoleon fish drift past, its bulk casting a moving shadow over the reef, it becomes clear that protection does not always look gentle. Sometimes it looks like a mouth capable of breaking what needs to be broken. Sometimes the reef needs a presence that says without noise or drama that certain excesses will not be tolerated. In a world that often frames conservation as preservation alone, the humphead wrasse reminds us that maintenance matters just as much. Growth requires pruning. Recovery requires relief from pressure. And sometimes the most effective repair tool is a very large fish with very strong jaws. Sometimes the reef needs a bouncer. At first, the reef barely seems to notice them. Starfish lie scattered across coral heads and sandy gaps like discarded ornaments, their arms draped loosely, their movements so slow they appear almost ornamental. In a healthy reef, they are part of the background, another texture among many. Fish pass overhead. Crustaceans shelter in cracks. Coral continues its quiet labor of building skeleton upon skeleton, year after year. Nothing about a single starfish suggests urgency or threat. That illusion is precisely what makes them so dangerous under the wrong conditions. Starfish are built for patience. Their bodies are simple in appearance but deeply specialized in function. They have no centralized brain, no fast reflexes, no obvious aggression. Instead, they operate through distributed nerve networks and hydraulic systems, moving their tube feet with steady, relentless control. Each step is powered by water pressure, not muscle speed, allowing them to cling tightly to surfaces and traverse complex terrain without fatigue. This mode of movement is slow, but it is tireless. And in ecosystems, tireless often beats fast. Most starfish species play relatively modest roles. They scavenge, graze on algae, or prey on small invertebrates, helping regulate populations without overwhelming them. In these contexts, starfish contribute to balance. They remove weak or exposed organisms, recycle nutrients, and occupy niches that prevent other species from monopolizing space. The reef absorbs their presence without disruption. But some species, given the right circumstances, can flip from background noise to dominant force. The crown of thorns starfish is the most infamous example. Its body bristles with venomous spines, a warning to predators and an effective deterrent to most would-be attackers. Beneath that armor lies a feeding strategy uniquely suited to dismantling coral reefs from the inside. This starfish does not bite or chew. Instead, it climbs onto living coral, everts its stomach outward through its mouth, and presses that stomach directly onto coral tissue. Digestive enzymes break down living polyps externally, liquefying them before absorption. What remains is bare white skeleton, stripped clean of life. One starfish feeding this way is a localized event. Annoying perhaps, but recoverable. Coral can regrow from surviving tissue, patching over damage given enough time. The disaster begins when starfish numbers surge. Under certain conditions, such as increased nutrient runoff from land, warmer water that boosts larval survival, or the loss of natural predators, crown of thorns populations can explode. Thousands of individuals can settle onto the same reef system, spreading outward like a slow-moving tide. Speed is irrelevant here. Starfish do not need to outrun coral or overwhelm it in a single assault. They advance incrementally, consuming coral surface after coral surface day after day, night after night. Their digestion does not pause. Their movement does not rush. They simply persist. In ecological terms, this is pressure applied continuously rather than force applied suddenly. Coral, which builds slowly and depends on stable conditions, cannot keep pace. As starfish consume coral, the reef's architecture begins to dissolve. Coral skeletons are not just decoration. They form the physical framework of the reef, creating crevices, overhangs, and vertical relief that countless organisms depend on. Fish use branching corals as nurseries. Invertebrates anchor themselves to hard surfaces shaped by coral growth. Water flow is altered by reef structure, slowing currents and trapping nutrients. When coral dies, that structure erodes. Skeletons weaken, collapse, and eventually crumble into rubble. The loss of architecture cascades through the ecosystem. Species that relied on hiding places are exposed. Predation rates increase. Recruitment of juvenile fish declines. Algae colonize dead surfaces, further inhibiting coral recovery. The reef flattens both physically and biologically, becoming less complex and less productive. All of this unfolds without storms, without dramatic temperature spikes, without visible catastrophe from the surface. The water remains clear. The sun still shines. The damage is happening quietly, mouth to skeleton. Starfish thrive in these moments because their biology is tuned for opportunism. They reproduce by releasing enormous numbers of gametes into the water column, relying on chance encounters rather than parental care. Most larvae die, but during favorable conditions, survival rates spike dramatically. When that happens, entire cohorts settle simultaneously, creating dense populations almost overnight in ecological terms. Once established, their venomous spines and chemical defenses protect them from most predators, allowing them to feed with minimal interference. Even their apparent vulnerability is misleading. Starfish can regenerate lost arms, sometimes regrowing entire bodies from fragments if enough tissue remains. This regenerative ability makes them resilient to partial predation or injury, further tipping the balance in their favor during outbreaks. Attempts to control populations through manual removal often struggle against this resilience, requiring sustained effort to make meaningful impact. From within the reef, the experience is one of erasure rather than destruction. Coral polyps retract and die beneath spreading starfish stomachs. Fish abandon once familiar territories as shelter disappears. The soundscape thins. What was once a layered environment becomes simplified, stripped of vertical relief and biological diversity. The reef is still there, but it is no longer functioning as a reef. It is important to understand that starfish are not acting outside their evolutionary role. The crown of thorns did not evolve to destroy reefs. It evolved to exploit coral as a food source, regulated by predators and environmental limits under natural conditions. The disaster emerges when those regulating forces are removed or weakened. Overfishing of predators, nutrient enrichment from land, and climate-driven stress on coral all conspire to tip the balance. The starfish simply responds, doing what it has always done, but now without restraint. This is where the concept of builders becomes critical. Coral is a builder species. It constructs habitat over centuries, investing energy into skeletal growth that benefits not just itself, but entire communities. Its architecture supports life far beyond its own survival. When starfish consume coral, they are not just feeding. They are dismantling infrastructure. They are deleting the physical memory of the reef, removing the accumulated work of generations. In this light, the starfish outbreak is not merely a predation event. It is a systemic failure, a shift from construction to demolition. The reef does not collapse because one organism is aggressive, but because the balance between builders and erasers has been lost. Without enough forces to limit starfish numbers, deletion outpaces creation. Standing on a reef devastated by starfish, the absence is profound. Where coral once rose in complex forms, there is now rubble and algae. The reef still exists as a location, but its identity has been erased. Recovery, if it comes, will take decades and depends on a delicate sequence of events. Reduction of starfish numbers, stabilization of water quality, survival of coral recruits, and protection from further disturbance. None of these are guaranteed. The lesson embedded in this process is uncomfortable in its simplicity. Ecosystems do not always fail through sudden shocks. Sometimes they are unbuilt slowly and methodically by organisms that are neither fast nor dramatic. Starfish do not need to dominate through strength or speed. They dominate through time and numbers, through persistence applied to a structure that cannot defend itself. In a functioning reef, starfish are part of the background, one thread in a dense ecological tapestry. In a degraded system, they become the unraveling force, pulling at the very fabric of the habitat until it gives way. They remind us that creation and destruction are not always opposites. They can be two sides of the same biological process, separated only by balance. Not all builders create. Some delete. The seafloor looks solid at first glance, a mosaic of stone and shadow that seems immune to change. Light filters down in broken sheets, illuminating patches of reef where kelp once rose in thick, swaying columns. Now those columns are gone. What remains is exposure. Bare rock stretches outward like a stripped foundation, pitted and pale, interrupted only by movement so subtle it is easy to miss. The movement comes from mouths. Sea urchins do not arrive with drama. There is no sudden violence, no explosive moment that announces their dominance. Instead, they appear as a slow accumulation of round bodies armed with spines, wedged into cracks, clustered along ledges, creeping outward from shelter. They are ancient animals, echinoderms whose basic design has survived hundreds of millions of years with little modification. Radial symmetry, a hard shell, a mouth on the underside, equipped with a set of interlocking teeth known as Aristotle's lantern. This mouth never rests. It scrapes, grinds and chews with mechanical persistence, shaving away living tissue grain by grain. From the urchin's perspective, this is survival in its purest form. Urchins do not migrate. They do not store energy efficiently. They live in direct conversation with what grows around them, and that conversation is conducted through constant feeding. Each individual grazes a small area, but when predators are absent and numbers climb, those small areas overlap until the entire reef becomes a feeding surface. Kelp spores settle and are eaten almost immediately. Young blades are clipped before they can rise. Even holdfasts, the thick root-like anchors of mature kelp, are worn down over time. Nothing tall survives. Nothing complex endures. This is how an urchin baron is born. Not with a storm or a temperature spike, but with patience. A reef that once felt alive collapses into something eerily static. Without kelp, currents sweep across the rock unchecked, increasing erosion and washing away nutrients. Fish that depended on the forest for shelter vanish or become easy prey. Invertebrates lose attachment points and disappear. The soundscape changes too, though it is something only instruments or experienced divers notice. Healthy reefs crackle and hum with movement. Urchin barrens are quiet, acoustically hollow places where life has thinned to a whisper. What makes this transformation unsettling is how invisible it can be from above. The ocean surface remains calm. There is no discoloration, no obvious signal that something fundamental has shifted below. From the shoreline, everything looks normal. Yet beneath the waves, mouths are scraping all day, every day, turning three-dimensional ecosystems into flattened plains. It is destruction without spectacle, erosion driven by biology rather than weather. Sea urchins are not villains. Their success is rooted in effective design. Their spines deter many predators. Their tube feet, operated by a hydraulic water vascular system, allow them to cling tightly to rock even in strong surge. Their slow metabolism lets them survive long periods of scarcity, waiting out unfavorable conditions. In some species, individuals can live for decades, even centuries, growing slowly and steadily while continuing to feed. This longevity means that once an urchin population establishes dominance, it can hold that ground for an astonishingly long time. The key factor is balance. In a functioning ecosystem, urchins are kept in check by predators such as sea otters, lobsters, large fish, and humans. When those controls weaken, whether through hunting, disease, or habitat change, urchins slip their leash. They reproduce effectively, releasing clouds of larvae into the water column. Most larvae never survive, but enough do. Enough always do. When conditions align, recruitment spikes, and a reef can tip from kelp-dominated to urchin-dominated in a matter of years, sometimes even months. The visual contrast is stark. One side of a reef may still support towering kelp, filtered light, drifting fish, and suspended life. Just meters away, the barren begins. The boundary can be so sharp it feels artificial, like a line drawn across the ocean floor. On one side, movement and color. On the other, stone and spines. The only animation comes from urchins pivoting slightly as they feed, rotating just enough to bring fresh rock under their teeth. Urchins do not rush because they do not need to. Time is their ally. Each scrape removes a microscopic layer of plant tissue or algal film. Multiply that by thousands of individuals over years, and the result is total clearance. This grazing pressure is relentless precisely because it is unspectacular. There is no single moment to intervene, no dramatic collapse that demands attention. By the time the change is obvious, recovery becomes difficult. Kelp struggles to return to an urchin barren because young plants cannot survive long enough to rebuild structure. Without structure, predators have fewer places to hide or hunt, reinforcing the urchin's advantage. It is a feedback loop that locks the system into a degraded state. In some regions, barrens have persisted for decades, long outlasting the original trigger that caused the imbalance. The physiology of the urchin is perfectly suited to this kind of dominance. Its digestive system processes tough plant material efficiently. Its sensory world is simple but sufficient, relying on chemical cues and light sensitivity rather than complex vision. It does not need to see the forest it destroys. It only needs to feel the surface beneath it and detect food. In evolutionary terms, it is a specialist in persistence, not speed or intelligence. There is an uncomfortable lesson embedded here. Ecosystems do not always collapse in ways that feel catastrophic. Sometimes they erode quietly, driven by organisms doing exactly what they evolved to do. The sea urchin is not an invasive force in most of these systems. It is native. It belongs. The damage comes not from its presence, but from its release from control. Standing over an urchin barren, the absence is what dominates the scene. No swaying kelp blades, no darting fish, just rock, spines, and space. It feels unfinished, like a city after demolition crews have passed through, but before anything new is built. And yet, The wrecking crew is still there, still working, still scraping at a surface that can no longer grow. From a distance, it might be tempting to blame storms, warming water, or pollution. Those forces matter, but here the cause is more intimate. It is biological pressure applied slowly and continuously. Mouths scraping all day, teeth grinding without pause. Life undone not by a single disaster, but by persistence. The ocean does not always roar when it is being destroyed. Sometimes it is dismantled quietly, one bite at a time, until the silence itself becomes the evidence. Cold Pacific water presses in from every direction, heavy and unyielding, a place where heat drains from flesh faster than fear ever could. Light filters down in pale shafts, fractured by surface chop and tangled by long curtains of kelp that sway with the patience of something ancient. This is not an empty ocean wilderness. It is a dense neighborhood, layered and crowded, built vertically from rock to sunlight. And at its center drifts a creature that looks almost accidental, as if it wandered into the scene from another world entirely. The sea otter floats on its back, fur trapping air like a living life jacket, paws folded loosely over its chest, eyes half-lidded in a posture that reads as lazy, until you understand what this animal actually does to the ecosystem around it. The sea otter is not a top predator in the way sharks or orcas are. It does not chase down prey in open water or dominate through size and speed. Its power is quieter, more methodical, and far more destabilizing. It feeds almost constantly, burning enormous amounts of energy just to keep its internal temperature stable in water that would kill most mammals within minutes. Unlike seals or whales, it lacks a thick layer of blubber. Instead, it relies on the densest fur in the animal kingdom, a living insulation system that works only if it is obsessively maintained and continuously fueled by calories. That biological constraint forces the otter into a life of relentless consumption, and what it consumes reshapes entire coastlines. Beneath the otter, clinging to rock like armored landmines, are sea urchins. They are round, spined, and deceptively simple-looking, but they are among the most influential herbivores in the ocean. Urchins feed by grazing, scraping microscopic teeth across rock and plant tissue, slowly but relentlessly. When kelp spores settle and attempt to grow, urchins mow them down. When kelp forests are healthy, urchins hide in crevices, limited by predators and by the complexity of the habitat. But when that balance breaks, when nothing hunts the urchins, they emerge in the open by the thousands, turning vibrant underwater forests into what ecologists call urchin barrens, vast stretches of bare rock where almost nothing tall or complex can survive. The sea otter is the animal that stops that collapse. It dives repeatedly, using its sensitive whiskers to detect the faintest movements along the sea floor. When it finds an urchin, it does not swallow it whole or tear it apart with brute force. Instead, the otter surfaces, rolls onto its back, and reveals one of the most primitive and effective tools in the marine world: a rock. Held on its chest like a portable anvil, the otter places the urchin against it and hammers until the spines snap and the shell fractures, exposing the soft tissue inside. This behavior is not a trick or a novelty. It is a survival strategy passed down culturally, learned from mothers, and refined over generations. Different otter populations even favor different tools, a sign that this is not just instinct, but adaptation layered with experience. Every shattered urchin is one less lawnmower chewing through kelp. And because otters eat constantly, the effect compounds. An adult sea otter can consume a quarter of its body weight in food every single day. That means hundreds of urchins removed from the system over time, not in a dramatic purge, but through steady, grinding pressure. This kind of predation does not just reduce numbers, it changes behavior. Urchins become cautious. They retreat into cracks and shadows, grazing less aggressively, allowing young kelp to establish itself. Once kelp gains a foothold, it grows fast, racing upward toward light, unfurling blades that slow currents and trap sediment. As kelp forests rise, the environment transforms. What was once a flat, exposed seafloor becomes a three-dimensional city. Tall stalks sway like skyscrapers in slow motion, their canopies forming a ceiling that filters sunlight into green-gold patterns. Fish move in and out of the forest, using it as cover from predators. Juveniles find shelter among the blades, protected during the most vulnerable phase of their lives. Invertebrates cling to the kelp's surface, feeding on the constant stream of nutrients flowing past. Even the water itself changes, as kelp dampens wave energy, reducing coastal erosion and stabilizing shorelines. This is where the sea otter's role becomes impossible to ignore. It is not just eating prey, it is deciding what kind of world exists below the surface. Remove the otter, and the balance tilts hard and fast. Urchins explode in number, unchecked and fearless. Kelp is stripped away faster than it can regrow. Fish populations crash as shelter disappears. The entire food web simplifies, collapsing into a dull, low-productivity state. Add the otter back, and the system rebuilds itself, not because the otter constructs anything directly, but because it enforces limits. It acts as a biological contractor, regulating demolition and allowing growth to proceed. The effect ripples outward in ways that are not immediately obvious. Kelp forests are among the most productive ecosystems on Earth, rivaling tropical rainforests in their ability to convert sunlight into biomass. They draw carbon dioxide from the water and atmosphere, locking it away in plant tissue and sediments. When kelp disappears, that carbon cycling weakens, subtly shifting local chemistry and even influencing climate feedbacks. The presence of sea otters, therefore, reaches beyond the visible web of life and into global processes that operate on timescales far longer than an otter's lifespan. There is a cruel irony embedded in this story. The sea otter's importance was not fully understood until it was almost gone. During the fur trade era, otters were hunted relentlessly for their pelts, prized for their density and softness. Entire coastlines were stripped of otters in a matter of decades. What followed was not just the loss of a charismatic animal, but the unraveling of ecosystems. Historical accounts describe once lush kelp forests reduced to barren rock, fisheries collapsing, and coastal productivity plummeting. At the time, these changes were treated as unrelated problems. It took modern ecology to reveal the connective tissue, to show that one animal's absence had pulled the thread that held everything together. When otters were reintroduced in some regions, the recovery was dramatic but uneven. Kelp returned in patches, fish populations rebounded, and biodiversity surged. But the process was slow, fragile, and dependent on continued protection. Otters are still vulnerable to pollution, disease, and entanglement. Their survival is tightly linked to the health of coastal waters, making them both a solution and a warning. They can rebuild ecosystems, but only if the broader environment allows them to exist. Watching a sea otter drift among kelp fronds, cracking shells with casual precision, it is tempting to see only the surface behavior. A cute animal eating lunch. But beneath that scene is a cascade of cause and effect that reaches from the smallest algae to the shape of coastlines themselves. The otter does not dominate through fear or force. It dominates through appetite, persistence, and an unremarkable-looking rock used with relentless efficiency. That simplicity is what makes it so powerful. In ecological terms, the sea otter is a keystone species, an organism whose impact on its environment is disproportionately large relative to its abundance. But that phrase can feel abstract until you stand inside the kelp forest it protects, until you see the difference between a living underwater city and a silent, scraped wasteland. The otter does not just save kelp. It saves complexity. It saves interactions, niches, and futures that would otherwise never exist. Strip away the scientific language, and the truth becomes almost embarrassingly direct. One animal eats the right thing, in the right place often enough. Everything else gets to live. Remove that animal, and the neighborhood falls apart. In the cold, rolling waters of the Pacific, the sea otter floats on its back, cracking another urchin, unaware that each strike echoes far beyond its own survival. One animal, an entire city saved. The ocean looks empty from above, an expanse of moving blue that seems too vast to be shaped by any single life. But emptiness is an illusion created by scale. Beneath the surface, the sea is structured by invisible gradients of nutrients, temperature, and light, and few animals rearrange those gradients more profoundly than the humpback whale. Long before its tail breaks the surface or its breath erupts into the air, its influence is already spreading through the water, carried by currents and chemistry rather than motion alone. A humpback whale feeds low in the water column, often deep below the reach of sunlight. Here, dense layers of krill and small schooling fish concentrate around nutrient-rich zones where microscopic life thrives. These feeding grounds exist because of chemistry, not chance. Nutrients released from decaying organic matter sink into deeper layers, fueling blooms of plankton that form the foundation of marine food webs. The humpback enters this system not as a subtle participant, but as a force that consumes on a scale difficult to comprehend. Each feeding lunge engulfs tens of thousands of liters of water, straining prey through baleen plates that evolved specifically to harvest abundance rather than chase individuals. This feeding behavior is energetically expensive, yet astonishingly efficient. The whale's body, streamlined and muscular, is designed to convert momentum into intake. Grooves along its throat expand like an accordion, allowing its mouth to balloon outward, swallowing prey and water in a single motion. When the mouth closes, water is expelled, prey retained, and energy transferred into blubber that will fuel long journeys across entire ocean basins. This is not merely feeding. It is accumulation, the gathering of nutrients into a living vessel capable of transport. Once the feeding season ends, the whale does something few other animals can replicate at this scale. It leaves. Humpbacks migrate thousands of kilometers from cold, productive feeding grounds to warmer breeding and calving areas where food is scarce, but survival of young is higher. During this migration, the whale eats little or nothing. Instead, it burns the energy stored during its feeding months. As that energy is metabolized, nutrients are released back into the ocean, not where they were consumed, but far from their point of origin. This is where the whale becomes more than a predator. It becomes a vector. Through waste products released near the surface, humpbacks inject iron, nitrogen, and other limiting nutrients into sunlit waters where phytoplankton can use them. Phytoplankton are microscopic, but their role is monumental. They form the base of marine food webs and drive a significant portion of global carbon fixation. Their growth depends not only on light, but on access to nutrients that are often scarce in surface waters. Whale waste, rich and bioavailable, acts as fertilizer precisely where it is most effective. The result is a process sometimes described as the whale pump, though the term barely captures its reach. Nutrients that would otherwise remain locked in deep water or concentrated in distant regions are redistributed across migration corridors, feeding in one ecosystem, fertilizing another. Giant eats, giant travels, ocean changes. The simplicity of the sequence belies the complexity of its impact. Increased plankton productivity supports zooplankton, which feeds fish, which feeds larger predators. Carbon drawn down by plankton is transferred through the food web and ultimately sequestered, influencing atmospheric processes over time. This nutrient movement is not random. Humpback migration routes are remarkably consistent across generations, passed down culturally rather than genetically. Calves follow mothers along established paths, learning where to go and when. These routes become ecological arteries, repeatedly infused with nutrients year after year. Over time, the ocean adapts around these patterns. Regions frequented by whales can exhibit higher productivity than surrounding waters, not because of upwelling or currents alone, but because of biological transport layered on top of physical processes. The whale's sheer size amplifies this effect. A single humpback can weigh tens of tons. Multiply that by entire populations migrating annually, and the scale of nutrient movement becomes staggering. Before industrial whaling, when whale populations were far larger than today, this process operated at a level modern oceans have not experienced for generations. The reduction of whales was not merely the removal of animals. It was the dismantling of a planetary-scale nutrient redistribution system. What makes this role especially striking is that it operates almost invisibly. There is no dramatic scene marking the moment a whale fertilizes the sea, no obvious boundary where productivity begins or ends. The effects manifest gradually through increased plankton density, through healthier fish populations, through subtle changes in carbon cycling. These outcomes are easy to miss precisely because they are systemic rather than spectacular. The humpback's behavior reinforces this role further. Unlike some whales that remain mostly submerged, humpbacks spend significant time near the surface. Their frequent surfacing, breaches, and tail slaps are not just displays or communication signals. They physically mix water layers, contributing to small-scale turbulence that can redistribute nutrients and plankton. Even their movement through the water column creates vertical mixing, nudging nutrients upward in ways that complement chemical processes. Thermoregulation plays an indirect part as well. Humpbacks maintain body temperatures far above the surrounding water, a feat achieved through thick blubber and controlled blood flow. This metabolic heat drives high energy consumption, which in turn necessitates large-scale feeding. The whale's need to stay warm becomes a driver of ecological change, linking physiology to planetary function in a direct line. There is an irony here that is difficult to ignore. Whales are often framed as victims of climate change, vulnerable to warming seas, shifting prey distributions, and increased human activity. All of that is true. Yet at the same time, whales actively influence the climate system through their support of plankton communities that absorb carbon dioxide. Their presence strengthens one of the ocean's most important climate-regulating mechanisms. Remove them, and the system weakens. Protect them, and the system gains resilience. The story becomes even more compelling when viewed over evolutionary time. Whales evolved from land mammals, returning to the sea and gradually growing into giants. In doing so, they did not simply occupy a niche. They created one. Their bodies became tools for moving matter across ecosystems, connecting regions that would otherwise remain chemically isolated. This is not a coincidence. It is an emergent property of size, mobility, and metabolism interacting with ocean physics. In modern oceans, where whale populations are still recovering from centuries of exploitation, this function is diminished, but not lost. Each returning humpback represents more than a conservation success. It represents a reinstated process, a migrating nutrient reservoir, a living engine converting prey into productivity across thousands of kilometers. Watching a humpback surface, exhale, and slip back beneath the waves, it is tempting to focus on the spectacle of the animal itself. The massive flukes, the sheer grace of a body that large moving with such control. But the more profound story unfolds beyond sight. Nutrients consumed in cold, rich waters will soon nourish microscopic life in warm seas. Carbon will be drawn down. Food webs will strengthen. All without intention, without planning, without awareness. The whale does not know it is altering climate dynamics. It does not know it is fertilizing oceans or supporting fisheries. It eats because it must. It migrates because it evolved to do so. The consequences ripple outward regardless. In an age that often searches for technological solutions to planetary problems, the humpback whale stands as a reminder that some of the most powerful climate mechanisms are biological. They are ancient, self-regulating, and astonishingly effective when left intact. The loss of such systems is not immediately catastrophic, but it is cumulative. The return of them is not dramatic, but it is transformative. Giant eats, giant travels, ocean changes. Whales are not just animals, they are moving climate engines. Shallow coastal waters often look deceptively calm, their surfaces broken only by ripples of wind and reflected sky. From above, seagrass meadows are nearly invisible, submerged fields stretching across sandy bottoms in quiet, orderly patterns. They do not rise like reefs or sway like kelp forests. They stay low, rooted and patient. Yet these meadows are among the most productive and important habitats in the ocean, and their health depends on an animal that moves through them with almost ceremonial slowness. The dugong enters this landscape not as a builder that adds material, but as an engineer that decides what survives by what it eats. A dugong glides just above the seafloor, its large body supported by neutral buoyancy rather than speed. It is shaped like a living question mark, heavy in the torso, tapering into a broad horizontal tail. Its skin bears scars accumulated over decades, evidence of long life in a shallow world filled with hazards. Unlike predators that scan for movement, the dugong's head is angled downward, its gaze fixed on the ground itself. This animal is not hunting. It is harvesting. Seagrass is not seaweed. It is a flowering plant, descended from terrestrial ancestors that returned to the ocean millions of years ago. It grows rooted in sediment, spreading through rhizomes that bind sand together and stabilize coastlines. Each blade photosynthesizes, capturing sunlight and storing carbon in below-ground tissues. Over time, seagrass meadows accumulate thick layers of organic material beneath the surface, locking away carbon for centuries. They also provide shelter and food for juvenile fish, crustaceans, and mollusks, forming nursery grounds that feed entire coastal ecosystems. But seagrass does not thrive if left entirely untouched. When growth becomes too dense or old blades accumulate faster than they can be replaced, oxygen levels near the sediment drop. Decaying plant matter can smother new shoots. Meadows become less resilient, more vulnerable to disease, storms, and temperature stress. This is where the dugong's role becomes essential. The dugong feeds almost exclusively on seagrass. Its mouth is uniquely adapted for this task, with a downturned snout and thick, muscular lips capable of uprooting plants with controlled force. As it feeds, the dugong plows shallow furrows through the meadow, pulling up entire plants, roots and all. To an untrained eye, this might look like destruction, a large animal tearing apart fragile habitat. In reality, it is selective pressure applied with evolutionary precision. By grazing repeatedly over favored areas, dugongs remove older, less productive plants and stimulate regrowth. New shoots emerge from remaining rhizomes, often growing faster and with higher nutritional value than ungrazed grass. This pattern of disturbance prevents any single species of seagrass from dominating, maintaining diversity within the meadow. The result is a patchwork of growth stages, from freshly cropped sections to mature stands, each supporting different communities of organisms. This grazing also alters sediment dynamics. As dugongs disturb the seafloor, they oxygenate upper sediment layers, reducing the buildup of harmful sulfides that can poison seagrass roots. Their feeding paths create subtle channels that influence water flow, redistributing nutrients and fine particles. Over time, these effects increase the meadow's stability rather than weaken it. The dugong is not removing the meadow. It is pruning it. The physical effort required for this lifestyle is immense. Seagrass is low in calories compared to animal prey, forcing dugongs to consume large quantities daily. Their digestive systems are elongated and specialized, extracting maximum energy from fibrous plant material. This diet shapes their behavior. Dugongs move slowly not because they are lazy, but because efficiency matters. Rapid movement would waste energy better spent eating. Their metabolism is tuned for endurance rather than bursts of activity, allowing them to feed for hours with minimal exertion. Thermoregulation plays a quiet but important role in this equation. Dugongs inhabit warm waters, but temperature fluctuations still affect their energy balance. Maintaining body heat requires constant intake of food, reinforcing their near-continuous grazing. In cooler conditions, dugongs increase feeding time or shift locations to warmer shallows, indirectly altering grazing patterns across the meadow. Even temperature becomes part of the engineering process. As dugongs feed, their influence spreads outward through the ecosystem. Fish larvae shelter among cropped seagrass, benefiting from reduced canopy density that allows better water circulation and oxygenation. Invertebrates colonize disturbed sediment, taking advantage of exposed surfaces. Predators follow, drawn by the abundance of prey. The meadow becomes more dynamic, more interconnected, because it is being used. Without dugongs, seagrass systems can tip towards stagnation. In regions where dugong populations have declined due to hunting, boat strikes, or habitat loss, meadows often grow unevenly or collapse entirely under stress. Overgrown sections become brittle. Disease spreads more easily. Storms uproot large areas that might have been more resilient under regular grazing. The absence of this single herbivore alters the fate of entire coastlines. The dugong's impact is magnified by its longevity. Individuals can live for many decades, returning repeatedly to the same feeding grounds. These repeated visits reinforce grazing patterns over time, shaping meadow structure across generations. Calves learn feeding routes by following their mothers, inheriting not just behavior but geography. This cultural transmission ensures that certain meadows receive consistent maintenance year after year, embedding dugong influence into the physical layout of the seafloor. There is a subtle irony in how overlooked this role can be. Conservation narratives often focus on dramatic predators or visually striking habitats like coral reefs. Seagrass meadows, flat and unassuming, rarely capture the same attention. Dugongs, gentle and slow, lack the spectacle of whales or sharks. Yet their work is foundational. Without healthy seagrass, reefs suffer from increased sedimentation. Fisheries decline as nurseries disappear. Coastlines erode more quickly, losing natural buffers against storms. The dugong does not build walls or raise structures. It does not stack materials or carve shelters. Its engineering is subtractive, not additive. By removing biomass in the right places at the right times, it allows the system to function as intended. This is an ancient strategy, mirrored by grazing animals on land that maintain grasslands through feeding rather than construction. In both cases, the ecosystem depends on consumption to prevent collapse. Watching a dugong feed is an exercise in reframing assumptions. The animal moves slowly, almost lazily, stirring sediment clouds that drift away on gentle currents. There is no urgency, no aggression. Yet the cumulative effect of this behavior, repeated day after day, year after year, shapes landscapes larger than the animal itself. Meadows persist. Carbon remains stored. Life finds space to grow. In evolutionary terms, the dugong represents a lineage that chose plants over prey, patience over pursuit. That choice shaped not only its body, but entire coastal ecosystems. Its disappearance would not cause immediate catastrophe. The water would remain blue. The sand would still lie in place. But over time, the absence would be felt in thinning fish populations, eroding shorelines, and weakened food webs. The loss would be quiet, incremental, and profound. There is something deeply instructive in this. Not all essential work in nature is dramatic. Not all engineers are builders in the human sense. Some shape the world simply by eating, guided by instincts honed over millions of years. The dugong does not know it is maintaining nurseries or stabilizing sediments. It eats because it must. The ecosystem responds because it has evolved to do so. In shallow coastal waters, beneath calm surfaces and shifting light, the dugong continues its slow passage across seagrass fields. Each bite removes a plant, but each removal makes space for renewal. In a world often obsessed with creation as an act of addition, the dugong reminds us that balance often comes from restraint, from selective loss that enables long-term growth. The ocean's most important work is sometimes just eating plants. The shallow water brightens as the seabed rises, sunlight sharpening into clear bands that slide across sand and grass. Here, the ocean feels less like an abyss and more like a field, an open space shaped by light, sediment, and growth rather than depth and pressure. Seagrass spreads outward in dense mats, blades bending gently with each passing swell. Algae cling to hard surfaces nearby, competing for space wherever light reaches. This is not a static environment. It is a system that clogs easily if left alone, and one of its most effective maintenance workers arrives without noise, cutting tools, or urgency. A green sea turtle glides in low, its shell casting a slow-moving shadow over the grass. Unlike predators that announce change through absence, green turtles shape ecosystems through selective removal. Their bodies are built for endurance rather than speed. Their flippers powerful but unhurried, moving with a steady rhythm that reflects an energy budget tuned for long-term grazing rather than pursuit. As juveniles, green turtles are omnivorous, sampling invertebrates and small animals as they grow. But as adults, They undergo a dietary shift that fundamentally alters their role in coastal ecosystems. They become herbivores, specializing in seagrass and algae, transforming from opportunistic feeders into living maintenance crews. The turtle lowers its head and bites cleanly through a blade of seagrass, then another, cropping rather than uprooting. This distinction matters. Where dugongs plow and excavate, turtles trim. Their jaws are serrated, adapted to shear plant material efficiently without tearing up the sediment below. Each bite removes older leaf tissue while leaving roots and rhizomes intact. The turtle moves forward slowly, feeding in lanes that are subtle at first but unmistakable over time. These grazing paths are not signs of damage. They are signs of regulation. Seagrass, like all plant communities, thrives under the right amount of pressure. Without grazing, blades grow long and dense, shading their own base and reducing light penetration. Old leaves accumulate, decay accelerates, and oxygen levels near the sediment drop. Disease spreads more easily through crowded stands. Growth slows. Productivity declines. Green turtles interrupt this cycle through repeated visits, returning to the same feeding grounds over months and years, trimming growth before it becomes a liability. This behavior increases the overall productivity of the meadow. Cropped seagrass responds by producing new shoots that are shorter, more nutrient-rich, and more efficient at photosynthesis. These younger blades support higher rates of growth and recovery, making the meadow more resilient to storms, temperature fluctuations, and sediment disturbance. The turtle does not fertilize directly, but by stimulating regrowth, it enhances the plant's ability to capture and store carbon, reinforcing one of the ocean's most important carbon sinks. The effects extend beyond the grass itself. Shorter seagrass improves water flow through the meadow, increasing oxygenation and reducing the buildup of harmful compounds in the sediment. Juvenile fish and invertebrates benefit from this balance, gaining both shelter and access to food without being trapped in stagnant conditions. Predators patrol the edges, drawn by abundance rather than chaos. The meadow remains open, functional, alive. Green turtles also play a crucial role along reef edges and coastal hard grounds, where algae compete aggressively with corals and other slow-growing organisms. Algae grow fast, especially in nutrient-rich waters, and can smother coral by blocking light and space. Many reef systems depend on herbivores to keep algae in check, and green turtles contribute to this control by grazing on macroalgae in shallow zones. Their feeding reduces algal dominance, preventing reefs from becoming overgrown and allowing corals and other calcifying organisms to maintain their foothold. This is not a dramatic intervention. Algae do not vanish overnight. But persistent grazing shifts the balance of competition. It slows algal expansion just enough for corals to recover from stress, settle new recruits, and rebuild structure. In this way, turtles influence both plant and animal communities across multiple habitats, linking seagrass meadows to reefs through shared pressure rather than movement. The turtle's physiology supports this role with quiet efficiency. Its digestive system is adapted to process fibrous plant material, relying on microbial fermentation to extract nutrients. This process is slow, requiring long retention times and steady intake. As a result, green turtles feed for extended periods, often resting between bouts of grazing to conserve energy. Their metabolism reflects a strategy of consistency rather than intensity, allowing them to maintain their ecological function over decades. Thermoregulation subtly shapes where and how turtles work. Green turtles are ectothermic, their body temperature tied to their environment. Warmer waters increase digestive efficiency and activity levels, while cooler conditions slow them down. As temperatures shift seasonally, turtles adjust their grazing patterns, concentrating effort where conditions allow maximum efficiency. These adjustments redistribute grazing pressure across the landscape, preventing any single area from being overworked or neglected. Migration adds another layer to this influence. Green turtles travel between feeding grounds and nesting beaches, sometimes crossing vast distances. While feeding occurs primarily at established sites, migration connects populations and behaviors across regions. Knowledge of productive meadows is passed down through experience, with turtles returning to familiar locations year after year. This fidelity ensures that certain habitats receive consistent maintenance over long periods, embedding turtle influence into the structure of coastal ecosystems. When turtles disappear, the consequences unfold gradually. Seagrass grows unchecked, becomes less productive, and eventually collapses under stress. Algae spread more aggressively across reefs and hard substrates, crowding out slower-growing species. Sediments destabilize as roots weaken. Fish nurseries shrink. None of this happens suddenly. There is no single moment of failure. Instead, systems clog, overwhelmed by excess growth that no longer cycles efficiently. The irony is that these environments often look healthy at first glance. Dense seagrass can appear lush. Thick algal cover can look vibrant. It takes time and ecological understanding to recognize when abundance has tipped into dysfunction. Green turtles act before that tipping point, removing just enough biomass to keep systems moving. Their shells bear witness to this long-term role. Scarred by encounters with predators, boats and reefs, each shell represents decades of movement through coastal landscapes. These animals are not transient visitors. They are fixtures, returning again and again to the same fields, trimming, shaping, maintaining. Their presence is a form of memory encoded in behavior rather than structure. From an evolutionary perspective, the green turtle occupies a rare niche. Large-bodied marine herbivores are uncommon, especially ones capable of moving between habitats and exerting sustained pressure over time. This combination of size, diet, and longevity gives turtles a unique ability to influence ecosystems without overwhelming them. They are neither grazers that erase vegetation, nor passive residents that allow stagnation. They operate in the narrow band where removal promotes renewal. Watching a green turtle feed can feel almost anticlimactic. There is no chase, no burst of speed, no visible conflict. Just a mouth opening and closing, a slow drift forward, a trail of trimmed grass left behind. But this simplicity is deceptive. The cumulative impact of these actions shapes coastlines, supports fisheries, stabilizes sediments, and influences carbon storage. The turtle does not build reefs or plant meadows. It keeps them working. In a world increasingly defined by excess, where nutrients overload systems and unchecked growth leads to collapse, the green turtle represents an older logic, one in which balance is maintained through constant, modest intervention. Not dramatic solutions, but daily maintenance. Bite by bite, meadow by meadow. As the turtle lifts off the seafloor and glides toward another patch of grass, its work continues invisibly behind it. New shoots will grow. Water will flow more freely. Fish will settle where shelter and oxygen align. The system will remain open rather than clogged, productive rather than stagnant. A green sea turtle does not look like an engineer. It carries no tools. It leaves no monuments. Yet through repetition, patience, and appetite, it manages landscapes larger than itself. It is not just part of the environment. It is one of the forces that keeps it functioning. A turtle is a living landscape manager. The seafloor rarely announces change. From above, it looks settled, a broad plain of sand or silt that seems shaped only by tides and storms. But down where light thins and gravity presses life flat against the bottom, the ocean floor is anything but stable. It is a living surface, constantly rearranged by the animals that depend on it. Few of those animals reshape it as persistently or as quietly as stingrays. A stingray moves like a shadow pressed into the sand. Its body is wide and flattened, wings rippling with slow, fluid strokes that barely disturb the water above. Eyes sit high on its head, watching the world while the mouth remains hidden underneath, sealed against the seabed. From a distance, it looks passive, almost decorative. That impression lasts only until it feeds. The ray settles, hovering inches above the sand. Then the bottom erupts. A sudden burst of motion sends sediment billowing outward in a cloud, grains lifted and suspended as if the seabed itself has exhaled. The ray plunges its head downward, using powerful pectoral fins and hydraulic suction to excavate the substrate. In seconds, a pit appears where smooth sand once lay. This is not random disturbance. It is targeted excavation, guided by senses tuned to detect life buried beneath the surface. Stingrays hunt prey that hides rather than flees. Worms, clams, crustaceans, small fish, organisms that rely on sand for protection. To find them, rays use electroreception, detecting the faint electrical signals produced by muscle contractions and nerve impulses. This sensory system allows them to map the invisible, to locate prey without sight or sound. Once detected, the ray digs with intent, scooping sand aside, uncovering what the substrate was designed to conceal. Each feeding event leaves a mark. Shallow craters, deeper pits, elongated trenches etched into the seafloor. These scars vary in size depending on the ray species, the prey pursued, and the sediment type. In some areas, especially shallow coastal flats, the bottom becomes a mosaic of depressions and ridges, evidence of repeated foraging. To the untrained eye, it may look like damage. To the ecosystem, it is renewal. These excavations alter microhabitats in ways that ripple outward. Freshly disturbed sand exposes buried organic material, making nutrients available to microorganisms and invertebrates. Oxygen penetrates deeper into the sediment, changing chemical conditions that influence which species can survive. Some organisms, adapted to stable, undisturbed sand, are displaced or exposed to predators. Others thrive in the newly opened space, colonizing pits and trenches as temporary shelters or feeding grounds. Small fish move in quickly, picking through loosened sediment for overlooked prey. Crabs and shrimp take advantage of exposed surfaces. Microbial communities shift, responding to altered oxygen levels and nutrient availability. Over time, as currents soften the edges of pits and refill them with drifting sand, the habitat resets, ready for the next round of excavation. This cycle repeats endlessly, driven by hunger rather than intention. The stingray's body is engineered for this role. Its flattened shape allows it to generate downward force, pinning prey and displacing sediment efficiently. Spiracles behind the eyes draw in water while the mouth remains buried, preventing clogging during feeding. Teeth are adapted to crush hard-shelled prey, capable of breaking through armor that protects clams and crustaceans. Every feature reinforces the ray's ability to dig, uncover, and consume. What makes this behavior ecologically significant is scale. A single ray can excavate dozens of pits in a day. Multiply that by populations spread across estuaries, lagoons, and continental shelves, and the cumulative effect becomes immense. Entire seafloors are reworked repeatedly, not by geological forces, but by animals foraging for food. In some environments, ray bioturbation rivals that of storms in shaping sediment structure, though it operates continuously rather than episodically. This constant remodeling prevents the seabed from becoming compacted and stagnant. Without disturbance, fine sediments can seal off deeper layers, limiting oxygen exchange and trapping nutrients below. Ray digging breaks this seal, keeping sediments loose and chemically dynamic. This benefits many benthic organisms, particularly those that rely on oxygenated conditions or feed on freshly exposed material. Yet not all species benefit equally. Animals that depend on camouflage or shallow burial for protection face increased risk when rays pass through. Prey is uncovered. Hiding places are destroyed. In this sense, stingrays function as selective pressure, favoring species that can quickly rebury, relocate, or exploit disturbed ground. The seafloor community becomes shaped by the expectation of disturbance, evolving in response to a landscape that never fully settles. The stingray itself operates within constraints. Feeding requires energy, and digging is costly. Rays must balance the effort of excavation against the reward of prey, selecting areas where success is likely. This creates patterns of disturbance rather than uniform chaos. Certain zones become heavily worked, others left relatively untouched, depending on prey availability and sediment type. The result is spatial complexity, a patchwork of conditions that supports greater biodiversity than a uniform bottom ever could. Thermal conditions influence this process as well. In warmer water, ray metabolism increases, leading to more frequent feeding and more intense sediment disturbance. In cooler conditions, activity slows, allowing sediments to stabilize temporarily. Seasonal shifts in ray behavior thus translate into seasonal rhythms on the seafloor itself. cycles of disruption and recovery tied to temperature and energy balance. Migration adds another layer. Some stingray species move between habitats over the year, shifting their foraging impact from shallow flats to deeper waters or vice versa. These movements redistribute disturbance across regions, preventing any single area from being overworked. The seafloor experiences waves of remodeling that track animal movement rather than physical tides. From a distance, these processes are invisible. Satellites cannot detect pits a few centimeters deep. Surface observations reveal nothing of the work being done below. Yet for the organisms living in and on the sediment, these changes define daily reality. Shelter appears and disappears. Food is uncovered and consumed. Chemical gradients shift. The bottom is not a passive foundation. It is a dynamic workspace. There is a temptation to view ecosystems as static backdrops upon which animals act. Stingrays invert that perspective. Their feeding behavior demonstrates that animals are not just inhabitants of habitats. They are agents that build, erase, and rebuild physical environments through routine actions. No planning, no foresight. Just biology playing out at scale. In areas where stingrays decline, the absence of this disturbance is noticeable over time. Sediments compact. Oxygen penetration decreases. Certain prey species proliferate unchecked while others decline. The bottom becomes smoother, more uniform, less diverse. The loss is subtle, easily overlooked, but consequential. Without the steady churn of excavation, the system loses flexibility. The stingray does not aim to engineer habitat. It does not modify the environment for the benefit of others. It feeds because it must, guided by senses refined over millions of years. The ecosystem responds because it has evolved under this pressure. Remove the ray, and the response changes. The system drifts towards stillness, and stillness in sedimentary environments often leads to decline. Watching a stingray feed is watching construction in reverse. Instead of adding material, it removes it. Instead of erecting structures, it opens space. But the outcome is not destruction. It is renewal through disturbance, diversity through disruption. The pits left behind are not scars. They are opportunities. As the ray lifts off the bottom and glides away, sediment settles slowly, particles drifting back into place. The pit remains for a while, a shallow depression that will host new interactions before it fades. Somewhere nearby, another ray descends, another excavation begins, and the cycle continues. The seafloor is not finished. It is never finished. It is shaped and reshaped by the animals that depend on it. One bite, one dig, one plume of sand at a time. The seabed is a work site. The reef never truly sleeps, but its busiest workers rarely draw attention. While large fish patrol the water column and corals quietly build their limestone cities, the real turnover happens closer to the ground, in the shadows where fragments settle and decay begins. Here, among rubble, sand, and broken shells, crabs move sideways through the ecosystem like living tools, part sanitation crew, part demolition team. Their work is constant, unglamorous, and absolutely essential. Dead material accumulates quickly in shallow marine systems. Fish die. Algae detach. Coral branches snap during storms. Bits of organic matter rain down from above, settling into crevices and low-flow zones where oxygen is limited. Left alone, this material would rot, fueling bacterial blooms that consume oxygen and release toxic byproducts. In extreme cases, shallow habitats can slip into hypoxic conditions, where life struggles to breathe. Crabs are among the first responders to this problem, converging on decay with astonishing speed. A crab detects opportunity through chemistry rather than sight. Its sensory world is tuned to dissolved signals drifting through the water, molecules released by damaged tissue or decomposing flesh. These cues spread quickly, and crabs follow them unerringly, emerging from hiding places to investigate. When they arrive, they do not discriminate. Fish carcasses, dead invertebrates, discarded molts, fragments of algae. All are processed through powerful claws and efficient mouthparts. Consumption begins almost immediately, breaking complex organic matter into smaller pieces that can be further recycled by microbes and detritivores. This rapid scavenging changes the trajectory of decay. Instead of a single mass of rotting material dominating a patch of reef or seafloor, energy is redistributed through multiple pathways. Crabs convert waste into biomass, which then becomes food for predators. Nutrients are released gradually rather than explosively, reducing the risk of oxygen depletion. The system stays breathable, chemically balanced, functional. Crabs excel at this role because of their physiology. Their exoskeletons protect them from sharp debris and opportunistic predators while they feed in exposed areas. Their claws are versatile tools, capable of tearing, crushing, and manipulating material with precision. Some species specialize in cracking shells, others in shredding soft tissue, still others in scraping algae from hard surfaces. Together, they form a distributed cleanup network, each species addressing a different category of waste. But scavenging is only half of their impact. Crabs are also inveterate movers of matter. As they forage, they dig into sediment, wedge themselves beneath rocks, and flip objects far larger than their bodies. A single crab lifting a stone may seem trivial, but across a reef or tidal flat, these actions accumulate. Rocks that once lay flat are overturned, exposing shaded surfaces to light and oxygen. Burrows open and collapse. Sediment is displaced and resettled. Microhabitats appear and vanish. This physical rearrangement alters who lives where. Under a flipped rock, organisms adapted to darkness and moisture suddenly face exposure, while algae and sessile invertebrates gain new real estate. Small fish and shrimp exploit freshly uncovered hiding spots. Predators take advantage of exposed prey. Over time, the constant churning prevents any single microhabitat from becoming permanent or monopolized. Diversity persists because stability never becomes absolute. Crab digging plays a similar role in soft sediments. Burrows aerate the substrate, allowing oxygen to penetrate layers that would otherwise become anoxic. This oxygenation supports worms, microbes, and small invertebrates that form the base of benthic food webs. It also influences nutrient cycling, promoting processes that convert waste products into forms usable by plants and plankton. The sediment remains chemically active rather than sealed and stagnant. Even the crab's waste contributes to this system. Fecal pellets, rich in partially digested organic matter, are quickly colonized by bacteria and consumed by smaller detritivores. Nothing lingers for long. Material moves, transforms, re-enters circulation. The reef avoids the ecological equivalent of clutter. Crabs themselves occupy an unusual position in food webs. They are consumers, recyclers, and prey all at once. Fish, octopuses, birds, and larger crustaceans feed on them, transferring the energy crabs gathered from waste back into higher trophic levels. In this way, scavenging does not remove energy from the system. It redirects it. Behaviorally, crabs are relentless. Many species are active day and night, adjusting activity patterns to avoid predators rather than resting completely. Their sideways gait allows quick retreats into crevices. Regeneration of lost limbs reduces the cost of risky behavior, encouraging bold foraging even in exposed areas. This persistence ensures that cleanup and rearrangement continue under almost all conditions. Environmental stress amplifies their importance. After storms, mass die-offs, or coral bleaching events, organic debris can overwhelm systems. Crabs respond by increasing feeding activity, drawn by chemical signals that spike during disturbance. Their populations may surge temporarily, accelerating the breakdown and redistribution of material. Without them, post-disturbance environments would linger in decay, delaying recovery. There is a subtle irony here. Crabs are often perceived as messy, opportunistic, even destructive. They tear things apart. They dig holes. They steal food. Yet those very behaviors are what prevent shallow ecosystems from choking on excess. Cleanliness, in ecological terms, does not mean tidiness. It means throughput. It means nothing stays unused long enough to become toxic. The scale of crab influence becomes clearer when it is absent. In systems where crab populations are reduced, dead matter accumulates. Algal mats thicken. Sediments compact and lose oxygen. Certain opportunistic species dominate while others disappear. The reef or flat does not collapse immediately. It suffocates slowly, burdened by its own waste. Crabs do not coordinate. There is no central plan. Each individual acts according to hunger, instinct, and immediate opportunity. Yet the collective outcome resembles a managed system, one where waste is processed, space is reorganized, and energy continues to flow. This is emergent order, produced not by design, but by countless small actions repeated over time. Watching a crab at work requires patience. It wedges a claw under a fragment, strains, flips it, then disappears beneath. Moments later, a small fish darts into the newly exposed space. A snail retreats. Sediment clouds briefly, then settles. The scene resets, altered in ways that only become obvious with time. Crabs remind us that ecosystems are not maintained solely by grand processes or iconic species. They depend on legions of small workers performing tasks that seem insignificant in isolation. Scavenging, digging, moving things around, preventing buildup, keeping pathways open. In shallow marine systems, waste is not an inconvenience. It is a threat. And the animals that deal with it are not optional. They are foundational. Crabs, with their armored bodies and relentless habits, keep the system breathing, turning decay into opportunity and disorder into motion. They do not build reefs or grow forests. They make sure those structures do not collapse under their own leftovers. In doing so, they occupy a role that is both humble and profound. Crabs keep the system from drowning in its own waste. The reef looks solid from a distance, a mass of stone and coral locked in place by time. But move closer to the bottom, where light fades into angled beams and shadows deepen beneath overhangs, and the illusion breaks. This is not a fixed landscape. It is a maze of openings, cracks, ledges, and hidden chambers, and survival depends on who controls them. Among the most committed architects and defenders of these spaces is the lobster, an animal whose life is shaped less by open water than by the availability of shelter. A lobster rarely ventures far without knowing exactly where it will retreat. Its body, armored but not invincible, is built for close quarters. The exoskeleton protects against abrasion and minor attacks, but it is heavy, inflexible, and periodically shed. During molting, the lobster becomes soft and vulnerable, its defenses temporarily stripped away. At that moment, open ground is lethal. Only a secure den offers survival. This biological constraint makes shelter not a convenience but a requirement. Lobsters seek out crevices in rock, gaps beneath coral heads, or burrows they excavate themselves in sediment. These dens are not random hiding places. They are carefully chosen for size, depth, and orientation. A good bunker allows the lobster to back in tail first, presenting its armored front and powerful claws outward toward any threat. This posture turns the den into a defensive stronghold, where a single individual can hold off predators far larger than itself. Once occupied, a den becomes more than a hiding place. It becomes territory. Lobsters recognize and defend their shelters aggressively, engaging in ritualized displays and physical confrontations to maintain control. Antennae lash. Claws are raised and locked. Strength, size, and endurance are tested. These contests are costly, but losing access to shelter is often fatal, especially for smaller or recently molted individuals. As a result, the value of a good den shapes lobster behavior as strongly as hunger or reproduction. This competition creates what can be described as a territory economy. Shelters are limited resources, unevenly distributed across the reef. Where rock is fractured and complex, dens are plentiful, and lobster populations can be dense and stable. Where structure is sparse, individuals are forced into closer competition, increasing aggression and mortality. In this way, the physical architecture of the reef directly controls population dynamics. Lobsters do not merely occupy these spaces, they modify and maintain them. Sediment is cleared from entrances. Loose rubble is pushed aside or repositioned to improve cover. Over time, A well-used den becomes more defined, its entrance smoothed by repeated use, its interior shaped to the occupant's body. This maintenance extends the life of the shelter, making it more effective not just for the current resident, but for future ones. Because lobsters are long-lived and site-faithful, dens can persist across generations. When a lobster abandons a shelter, whether due to death, displacement, or migration, the space rarely remains empty for long. Other lobsters move in. Fish use it as a temporary refuge. Octopuses, eels, and crabs may occupy it between residents. The den becomes a shared asset within the ecosystem, its existence increasing local biodiversity simply by providing structure. This reuse amplifies the lobster's impact beyond its own survival. By maintaining and defending shelters, lobsters contribute to the three-dimensional complexity of the reef, a factor strongly linked to species richness and resilience. Complex habitats provide more niches, reduce direct competition, and buffer ecosystems against disturbance. In this way, lobster behavior supports life well beyond its immediate needs. The importance of shelter becomes most apparent during vulnerable periods. Molting transforms a lobster from armored tank to soft-bodied prey. During this time, it retreats deep into its den and remains hidden until its new shell hardens. Without a secure bunker, molting becomes a gamble few lobsters survive. This dependence reinforces the evolutionary pressure to secure and defend quality housing. Shelter also plays a critical role in reproduction. Mating typically occurs shortly after a female molts, when her shell is still soft. To protect her during this period, a male often allows the female to share his den, guarding her from predators and rival males. This temporary cohabitation ties reproductive success directly to territory ownership. Males with better shelters are more likely to attract and successfully mate with females, linking real estate quality to genetic legacy. Predators understand this dynamic as well. Octopuses probe den entrances with flexible arms, testing defenses. Large fish attempt to flush lobsters from crevices. In response, lobsters reinforce their bunkers, using body position, claw display, and the narrow geometry of the entrance to their advantage. The den becomes a battlefield defined by angles, reach, and leverage rather than speed. This interaction shapes the behavior of other species. Fish learn which shelters are defended and which are vacant. Smaller animals time their movements around lobster activity, exploiting moments when dens are temporarily unoccupied. The reef becomes a living map of occupied and unoccupied real estate, constantly shifting as individuals move, grow, or disappear. The lobster's sensory world supports this lifestyle. Its long antennae extend far beyond its body, detecting movement and chemical cues in the water. These sensors allow it to assess threats without exposing itself, reinforcing a strategy built around staying close to shelter. Vision is secondary. Touch and chemical detection dominate, perfectly suited to a life spent navigating tight spaces rather than open water. Environmental changes can disrupt this entire system. When reefs are damaged by storms, pollution, or destructive fishing practices, shelter availability drops. Rocks are flattened. Coral heads collapse. Crevices fill with sediment. Lobsters are forced into the open or into overcrowded dens, increasing competition and mortality. Populations decline, not because food disappears, but because housing does. This highlights a critical but often overlooked aspect of reef health. Structures are not just coral. They are the spaces between coral, the gaps, holes, and shadows that animals use to survive. Protecting reefs means protecting architecture at multiple scales, from towering coral heads down to fist-sized crevices. Lobsters illustrate this principle with unusual clarity. Their lives revolve around shelter to such an extent that removing structure is equivalent to removing the species itself. No amount of food can compensate for a lack of safe housing. This dependency makes lobsters sensitive indicators of habitat quality. Where lobsters thrive, structure remains intact. Where they vanish, something fundamental has been lost. Over time, the presence of lobsters can even influence how reefs recover. By maintaining dens and clearing sediment, they help keep rubble from smothering regrowing coral. Their scavenging removes decaying material that could fuel disease. Their shelters provide refuge for juvenile fish that later contribute to reef resilience. The effects are indirect, but cumulative. There is a stark simplicity to this system. Space controls survival. Access to shelter determines who lives long enough to reproduce, who grows large, and who passes on their genes. The reef is not just a feeding ground. It is a housing market, with limited inventory and constant competition. Watching a lobster emerge cautiously from its den at night, antennae sweeping the water, claws raised in readiness, it becomes clear that its confidence is rooted in proximity to shelter. It ventures only as far as it can safely retreat. Every movement is calculated against the distance back to its bunker. This is not fear. It is strategy refined over evolutionary time. When dawn approaches, the lobster returns, sealing itself back into stone. The den remains, waiting, a small fortress embedded in the reef's larger structure. Other animals pass by, aware of its presence, adjusting their own behavior accordingly. The architecture continues to shape life, even when the builder is hidden. The lesson extends beyond lobsters. In the ocean, as on land, survival is governed by access to space as much as access to food. Animals that control shelter control opportunity. They influence who can rest, who can reproduce, who can avoid being eaten. The physical layout of the environment becomes destiny. Reefs are often celebrated for their beauty, their colors, their abundance. But beneath that spectacle lies a quieter truth. Life underwater is negotiated through structure, through holes and ledges, through bunkers carved into rock and defended tooth and claw. Lobsters do not build reefs, but they make them livable. They turn stone into shelter, shelter into territory, and territory into survival. Their presence reminds us that ecosystems are not just networks of feeding relationships. They are landscapes of opportunity shaped by access to space. Real estate controls life underwater. The reef edge looks chaotic at first glance, a scatter of rubble, sand, broken coral, and shifting shadows where nothing appears permanent. But beneath that apparent disorder lies a grid of ownership, a map of defended space enforced with extraordinary precision. The mantis shrimp does not simply live on the reef. It occupies it, carves into it, and controls it through architecture and force. In a world where shelter determines survival, this animal has turned burrow construction into a system of power. A mantis shrimp begins its story not with a hunt, but with a location. Before it ever strikes prey, before it ever raises its raptorial appendages in threat, it must secure a base. The burrow is not optional. It is the center of everything. Without it, the mantis shrimp is exposed, vulnerable to predators far larger than itself, and unable to exploit the reef efficiently. With it, the animal becomes dominant within a defined radius, a resident rather than a transient. Burrow selection is deliberate. Mantis shrimp assess sediment type, structural stability, proximity to prey-rich zones, and sightlines extending outward from the entrance. Some species prefer U-shaped burrows in sand that allow rapid retreat and multiple escape routes. Others occupy crevices in coral rubble or rock, modifying existing cavities rather than excavating from scratch. In both cases, the goal is the same: a defensible structure that channels threats through predictable angles and allows the shrimp to control engagement distance. Once selected, the burrow is not left as found. Maintenance begins immediately. Loose sediment is removed. Structural weak points are reinforced with shell fragments, stones, or coral chips. The entrance is shaped to match the occupant's body width, minimizing the gap an intruder could exploit. Over time, the burrow becomes a custom-fitted structure, molded by repeated use and constant repair. Storms may collapse portions. Other animals may attempt intrusion. Each disruption is met with rebuilding. This constant maintenance has ecological consequences. Burrow excavation redistributes sediment, aerating the substrate and exposing buried material to oxygen. Microorganisms respond. Nutrient cycling accelerates. Small invertebrates colonize disturbed areas, increasing prey availability not just for the mantis shrimp, but for neighboring animals as well. The burrow becomes a node of activity in an otherwise shifting landscape. From this base, the mantis shrimp feeds. Its hunting strategy depends entirely on proximity to shelter. Unlike wide-ranging predators, it does not roam far. Instead, it waits, positioned just inside the burrow entrance, eyes scanning independently, capable of tracking multiple targets at once. The shrimp's visual system is among the most complex known, with specialized receptors tuned to polarized light and subtle spectral differences. This sensory advantage allows it to detect movement and contrast even in cluttered reef environments. When prey approaches, the strike is instantaneous. Whether the mantis shrimp is a smasher or a spearer, its weaponry is calibrated for decisive force. Smashers deliver blows so fast they create cavitation bubbles, briefly generating heat and shockwaves that contribute to the impact. Spearers extend barbed appendages that impale soft-bodied prey with surgical accuracy. In both cases, the burrow is critical. It provides a stable platform from which to strike and an immediate retreat path once the attack is complete. Territory enforcement follows naturally. The mantis shrimp does not tolerate encroachment near its burrow. Competitors are met with displays first, a ritualized sequence of raised appendages and posture meant to assess strength without immediate violence. These interactions are not random aggression. They are negotiations over space. Only when displays fail does combat occur, and even then, the architecture of the burrow shapes the outcome. Narrow entrances limit angles of attack. Familiar terrain favors the resident. This enforcement stabilizes the surrounding community. When a mantis shrimp establishes territory, it creates predictable boundaries. Other animals learn where not to settle, which shelters are unavailable, which zones are risky. Smaller crustaceans avoid the immediate area. Fish pass overhead rather than linger near the entrance. This clarity reduces constant conflict and allows other species to organize themselves around fixed points of exclusion. The burrow also serves as a refuge during vulnerability. Mantis shrimp periodically molt, shedding their rigid exoskeletons to grow. During this period, their bodies soften, and their signature weapons become temporarily useless. Without a secure burrow, molting would be lethal. Inside, sealed from the outside world, the shrimp waits as its new armor hardens. The survival of this phase determines lifespan and reproductive success, tying burrow security directly to evolutionary fitness. Reproduction reinforces the importance of base control. Eggs are often laid and guarded within the burrow, where the resident can defend them aggressively. The burrow becomes a nursery, protected from predators and environmental stress. Successful reproduction is therefore not just about finding a mate, but about controlling safe space long enough for offspring to develop. Over time, these burrows accumulate history. Some are occupied by the same individual for years. Others are inherited, contested, or abandoned and reused. Each burrow represents invested labor and territorial assertion. The reef floor becomes a patchwork of influence, with mantis shrimp shaping not just their immediate surroundings, but the spatial logic of the ecosystem. The intimidation factor cannot be overstated. The mantis shrimp's reputation precedes it, even among animals without cognition in the human sense. Predators test boundaries cautiously. Many learn to avoid these burrows altogether. The shrimp's weaponry, capable of breaking shells and inflicting serious damage, enforces a kind of local order. Where it resides, space is respected. This has cascading effects. By controlling access to shelter and nearby prey, mantis shrimp indirectly influence population densities of other species. Some animals benefit from reduced competition. Others are excluded entirely. The result is not chaos, but structure, an emergent zoning system driven by force and architecture rather than cooperation. Environmental changes expose how fragile this balance can be. When reefs are flattened by storms, dredging, or destructive fishing, suitable burrow sites vanish. Mantis shrimp are forced into suboptimal shelters or exposed terrain. Their territorial control weakens. Feeding efficiency drops. Mortality rises. The loss of burrow builders contributes to a broader breakdown in spatial organization, making the reef more chaotic and less resilient. Conversely, in healthy systems with abundant structure, mantis shrimp populations thrive, and their burrows contribute to sediment turnover, nutrient cycling, and habitat complexity. Their presence is a sign of architectural integrity at small scales, the kind often overlooked in favor of large coral formations. What makes the mantis shrimp remarkable is not just its weaponry, but the way it integrates that weaponry into a broader strategy of place-based survival. It does not chase dominance across the reef. It builds it, one burrow at a time. It invests in location, defends that investment, and reaps the benefits through reliable feeding, protection, and reproduction. There is something almost architectural in this approach. The shrimp understands, through instinct rather than cognition, that control of space precedes control of resources. Food comes to those who can wait safely. Safety comes from structure. Structure must be defended. Watching a mantis shrimp retreat into its burrow after a strike, entrance partially blocked by debris it has arranged just so, it becomes clear that the reef is not governed solely by growth and consumption. It is governed by ownership, by defended space carved into sand and stone. The reef has landlords with hammers. The reef does not announce intelligence. It reveals it slowly, through patterns that only become obvious with time. A pile of shells where none should accumulate. Stones arranged in a way currents would never allow. An opening that appears and disappears between days, sealed one morning, open the next. These are not accidents. They are the architectural fingerprints of an octopus, an animal that does not merely hide in the environment, but edits it. An octopus approaches shelter the way a strategist approaches terrain. It does not accept the reef as it is. It evaluates. Crevices are tested for depth and escape routes. Overhangs are inspected for sightlines and current flow. The animal's body, soft and compressible, allows it to enter spaces far smaller than its apparent size, but it does not choose dens at random. A good den must do several things at once. It must block access from large predators. It must allow rapid exit in multiple directions. It must provide darkness without stagnation, protection without isolation. Once found, that space stops being part of the reef and starts becoming part of the octopus. The transformation begins immediately. Loose rocks are dragged into place, one arm at a time, gripped with suction cups capable of exerting precise force and feedback. Shell fragments, coral rubble, even discarded human debris are repositioned deliberately, stacked or wedged to narrow entrances and create choke points. These are not reflexive movements. Octopuses assess fit, adjust placement, and revisit arrangements repeatedly. If a current shifts debris out of alignment, it is corrected. If a predator probes the entrance, the barrier is reinforced. The den evolves. This construction serves multiple functions. Physically, it reduces the size of the entrance, forcing intruders into predictable angles where the octopus can strike or escape. Visually, it breaks up the outline of the opening, making it harder for predators to identify the den as occupied. Hydrodynamically, it alters water flow, preventing stagnant pockets while minimizing sediment intrusion. The octopus is not building walls, it is shaping gradients of risk. Over time, evidence of long-term residence accumulates. Outside many octopus dens lie middens, piles of shells from crabs, clams, snails, and other prey. These middens are not incidental. They represent repeated feeding from the same base, a sign that the octopus has claimed the area and successfully defended it over extended periods. Some middens grow large enough to become landmarks on the reef, visible signals of predation pressure that alter the behavior of surrounding prey species. Prey animals learn. Crabs skirt wide arcs around active dens. Snails alter grazing routes. Small fish adjust shelter use near octopus territory, avoiding areas where ambush is likely. The den becomes a predator hot zone, not because the octopus is always hunting, but because the environment itself has been redesigned to favor it. Risk is no longer evenly distributed. It is concentrated. This concentration has ripple effects. Areas immediately surrounding dens experience reduced prey density, while adjacent zones may see increased activity as animals shift their behavior. In this way, a single octopus can influence spatial patterns across a surprisingly large area, not by constant movement, but by static design. The reef reorganizes around the den. The octopus's intelligence underpins this capability. Its nervous system is unlike that of most animals, with a large proportion distributed throughout its arms. Each arm can explore, manipulate, and respond semi-independently, allowing the animal to interact with multiple objects at once. This decentralized control enables complex construction behaviors that would be difficult for animals relying on centralized processing alone. The octopus does not simply grab and move. It feels resistance, texture, and alignment in real time, adjusting its actions accordingly. Vision complements this tactile intelligence. Octopuses possess keen eyesight, capable of detecting contrast and movement even in low light. Combined with camouflage abilities that allow rapid changes in color, texture, and posture, the octopus becomes both architect and illusionist. The den does not merely block entry. It disappears into the background, its entrance masked by patterns that mimic surrounding rock or algae. The structure is functional and deceptive at the same time. Camouflage extends inside the den as well. The octopus often positions itself to blend seamlessly with the interior, reducing detection even if a predator peers inside. This integration of body and architecture blurs the line between organism and environment. The den is not a separate object. It is an extension of the octopus's strategy. Construction also serves social and reproductive functions. During mating periods, dens provide controlled environments where interactions can occur with reduced risk. Eggs, once laid, are guarded within these spaces, tended constantly by the female. She cleans them, aerates them, and defends the den aggressively until hatching. During this time, feeding may cease entirely. The den becomes a nursery, its design critical to the survival of the next generation. The cost of maintaining such a structure is high. Construction takes time and energy. Defending a fixed location increases vulnerability to persistent predators. Yet octopuses continue to invest in dens because the payoff is control. Control over when and how encounters occur. Control over escape routes. Control over the immediate ecological neighborhood. Environmental conditions influence den design. In areas with strong currents, entrances are reinforced differently than in sheltered lagoons. In sediment-heavy zones, barriers are adjusted to prevent collapse. Octopuses respond to local conditions with remarkable flexibility, altering construction techniques rather than relying on a single blueprint. This adaptability allows them to occupy a wide range of habitats, from coral reefs to rocky shores to seagrass edges. When an octopus abandons a den, the structure often persists. Other animals may move in, using the modified space as shelter. In this way, octopus construction contributes to habitat complexity even after the builder is gone. The reef retains the imprint of intelligence, embedded in rearranged stone and shell. The contrast becomes stark in environments where octopus populations decline. Without their dens, certain areas lose structural diversity at small scales. Shell middens disappear. Prey species redistribute differently. Predation pressure becomes more diffuse, altering food web dynamics. The absence of octopus is not just the loss of a predator. It is the loss of an environmental editor. What distinguishes octopus construction from that of other animals is intentionality. Crabs dig. Fish fan nests. Shrimp excavate burrows. But octopuses combine manipulation, assessment, and modification in ways that suggest planning rather than simple instinct. They do not merely respond to the environment. They anticipate how it will respond to them. This anticipation is evident in how entrances are blocked when the octopus leaves and reopened upon return. Rocks are not placed permanently. They are positioned for reversibility. The octopus remembers the configuration, returning to adjust it as needed. This temporal awareness adds another layer to the den's function, turning it into a dynamic structure rather than a static shelter. Watching an octopus construct or modify its den is watching cognition externalized. Decisions are made not only in neural circuits, but in the placement of objects. Strategy is encoded into the environment itself. The den becomes a physical memory, storing solutions to recurring problems like predator approach, current direction, and prey access. In this sense, The octopus challenges traditional distinctions between intelligence and behavior. It does not need tools in the human sense. It does not need social learning or language. It needs only the ability to shape space in ways that persist beyond the moment. And it does so with startling effectiveness. The reef, once seen as a backdrop, becomes a canvas. Stones become barriers. Shells become warnings. Openings become controlled interfaces between safety and risk. Every modification reinforces the octopus's dominance within its chosen zone. Predators recognize this dominance. Many fish hesitate to probe an octopus den, aware that reaching inside may provoke a sudden, coordinated response from multiple arms. Even animals larger than the octopus treat these spaces with caution. The den projects threat outward, extending the octopus's influence beyond its body. The cumulative effect is a localized restructuring of the ecosystem. Energy flow changes. Prey distribution shifts. Shelter availability alters. All because one animal decided not to accept the reef as given. The octopus does not just hunt prey. It engineers encounters. It does not just hide. It curates safety. Intelligence in this context is not an abstract quality. It is visible in stone and shell, in altered currents and redistributed risk. As the octopus settles into its den, entrance sealed behind it with deliberate precision, the reef around it adjusts. Some animals move away. Others take advantage of the new structure. The environment remembers the octopus even when it is still. Intelligence does not just hunt. It builds strategy into the environment. The reef does not rely only on stone to create boundaries. In many places, the most effective walls are alive, pulsing gently with the water, armed not with mass or hardness, but with chemistry. A sea anemone anchors itself to rock or coral, its soft body spreading outward like a flower caught mid-bloom, tentacles waving with deceptive calm. It looks fragile. It is anything but. Around this organism, invisible lines are drawn, lines that decide who may pass, who may stay, and who must keep distance. The anemone builds territory not by stacking material, but by enforcing consequence. Each tentacle is packed with thousands of stinging cells, microscopic weapons known as nematocysts, primed like loaded springs. These cells fire faster than almost any mechanical system in the animal world, injecting venom into anything that brushes against them. The reaction is instantaneous. Small fish convulse, invertebrates are paralyzed. Even larger animals recoil, learning quickly that contact comes at a cost. The anemone does not chase intruders or pursue prey across the reef. It simply exists, and that existence reshapes space. From this chemical barrier emerges a protected zone. The area immediately surrounding an anemone becomes hostile to most organisms, effectively cleared of casual traffic. Predators that might otherwise patrol a reef face a dilemma here. To approach means risking stings to eyes, gills, or soft tissue. Many choose avoidance over curiosity. The anemone's reach becomes a no-go radius, a biological moat enforced by pain rather than height. Yet within this danger zone, life flourishes selectively. Certain species evolve tolerance or immunity to the anemone's venom, allowing them to inhabit space denied to others. Most famously, anemone fish move among the tentacles with apparent ease, protected by specialized mucus that prevents nematocysts from firing. This adaptation is not trivial. It requires precise biochemical compatibility, a balance that must be maintained through constant contact. Without it, the fish would be killed like any other intruder. The result is a micro-territory of exclusion and privilege. Inside the tentacles, anemone fish gain shelter unmatched elsewhere on the reef. Predators cannot follow. Even animals that might normally prey on the fish hesitate, unwilling to endure repeated stings. The anemone becomes a living fortress, its walls flexible but absolute. In return, the fish provide services. They chase away certain predators, remove parasites, and increase water circulation around the anemone's body. Waste products contribute nutrients. The relationship is mutual, but the architecture belongs to the anemone. This fortress effect extends beyond one partnership. Other small invertebrates, including shrimp and crabs with similar tolerances, may share the space. Each species negotiates its position carefully, respecting boundaries enforced not by aggression, but by chemistry. The anemone does not need to recognize allies or enemies. Its venom applies equally. Survival depends on adaptation, not permission. On a broader scale, anemones influence reef layout by creating islands of safety amid exposed terrain. Fish distribution reflects this. Juveniles cluster near anemones, using them as reference points in an otherwise dangerous environment. Territories form around these structures, with dominance hierarchies influenced by proximity to protection. A reef without anemones distributes risk evenly. A reef with them becomes uneven, a patchwork of safe zones and lethal borders. This unevenness increases complexity. Predators adjust hunting routes to avoid stinging zones. Prey species alter movement patterns, sometimes taking longer, safer paths rather than direct routes through defended areas. Energy flow bends around anemones, creating eddies of interaction that shape who encounters whom. The reef's social geography shifts. The anemone's own biology reinforces its role as a static but powerful architect. Its body is anchored firmly, often remaining in the same location for years. Unlike mobile predators, it does not relocate to follow opportunity. Instead, opportunity comes to it. Plankton drift into its tentacles. Small fish blunder into reach. The anemone's success depends on positioning rather than pursuit. Where it settles matters enormously. Choosing that location involves trade-offs. Strong currents bring food, but increase physical stress. Sheltered zones reduce wear, but limit intake. Once attached, relocation is costly and rare. This makes the anemone a long-term feature of the reef, a fixed landmark around which ecological relationships accumulate. Over time, the surrounding community adapts to its presence, incorporating its defensive perimeter into daily life. The venom itself is finely tuned. Different species of anemone produce different toxin cocktails, targeting specific ion channels and neural pathways. These toxins are powerful enough to subdue prey quickly, preventing escape or struggle that could damage the anemone's soft body. For most animals, a single encounter is enough to imprint avoidance. Learning occurs at the population level. Areas around anemones become culturally known as dangerous, even among species incapable of individual memory in the human sense. This learned avoidance amplifies the anemone's influence. It does not need to sting every intruder. Its reputation does much of the work. Over time, the anemone shapes behavior beyond its physical reach, altering how animals navigate the reef. The presence of anemones also affects competition for shelter. In environments with limited crevices or coral structure, anemones provide alternative protection. Fish that might otherwise compete fiercely for holes or overhangs instead associate with anemones, reducing pressure on physical shelters. This redistribution of shelter demand can ease conflict and allow higher population densities than structure alone would support. When anemones disappear, these dynamics unravel. Fish lose safe havens. Predation rates increase. Juvenile survival drops. The reef becomes more dangerous, not because predators increase, but because protection decreases. The loss is subtle but measurable, especially in early life stages where shelter determines survival. Anemones themselves are not invulnerable. They can be damaged by storms, pollution, and temperature stress. Bleaching events, similar to those affecting corals, can strip anemones of their symbiotic algae, weakening them over time. When anemones decline, the walls they maintain collapse, opening territory that was once restricted. The neighborhood map is redrawn. There is a quiet irony in this system. The anemone builds safety not through cooperation but through threat. Its relationships are not based on trust, but on tolerance. Allies are those who can withstand its defenses. Enemies are everyone else. This creates a form of order that does not rely on mutual restraint or social behavior, but on biochemistry. In human terms, the anemone would seem antisocial, its boundaries absolute, its welcome limited to a select few. Yet, ecologically, this rigidity adds structure. It creates predictable zones of interaction, reducing chaos by clearly defining where certain activities can and cannot occur. In a crowded reef, clarity matters. Watching an anemone sway in the current, tentacles extended, it is easy to mistake stillness for passivity. But every movement reinforces its presence. Every drifting organism that veers away marks the edge of its influence. Every fish that shelters within confirms the effectiveness of its design. The anemone does not construct walls of stone or coral. It does not excavate or stack. It projects force outward through microscopic weapons, turning soft tissue into a barrier as real as any reef structure. Its architecture is chemical, its boundaries enforced through pain and paralysis rather than height or thickness. Over years, these living fortresses dot the reef, each one a node of altered behavior and redistributed risk. Together, they create a layered environment where not all space is equal, and where survival depends as much on where you are as on who you are. The reef is often described as a city full of builders and demolishers, engineers and opportunists. Sea anemones remind us that some of the most effective builders do not add material at all. They define space by exclusion, shaping life by deciding who cannot enter. Some builders use poison instead of bricks. The anemone does not live alone. Its tentacles sway with the slow rhythm of the reef, armed and waiting. But within that forest of venom lives a second presence, smaller, faster, and far more restless. Clownfish dart in tight arcs, flashing orange and white as they weave through stinging arms that would kill almost anything else. This is not coincidence, and it is not charity. It is tenancy, maintained through constant effort, constant defense, and constant tension. The anemone is the fortress. The clownfish are the occupants who make sure it keeps working. From the moment a clownfish settles into an anemone, the relationship becomes active rather than passive. Protection is not simply received, it is earned and maintained. The fish must acclimate carefully, brushing tentacles in controlled contact to build a protective mucus layer that prevents nematocysts from firing. This process is precise and risky. Too fast, and the fish is stung. Too slow, and it fails to integrate. Once complete, the clownfish gains access to one of the most exclusive shelters on the reef, a space almost no predator dares to enter. That shelter reshapes the fish's entire life strategy. Clownfish are poor swimmers compared to many reef fish. They lack speed, long-distance endurance, and the ability to outrun predators in open water. Without protection, they would be easy prey. Inside the anemone, those weaknesses no longer matter. The tentacles form an impenetrable barrier, turning vulnerability into advantage. Predators that could swallow a clownfish whole stop short, unwilling to trade a meal for repeated stings to eyes or gills. But protection is not a one-way transaction. The presence of clownfish alters the anemone's immediate environment in subtle but critical ways. Their constant movement through the tentacles increases water circulation, improving oxygen delivery and waste removal around the anemone's tissues. This matters for an organism that remains anchored in place, dependent on surrounding flow to maintain physiological balance. The fish become living pumps, their activity preventing stagnation inside the fortress. Clownfish also act as sentinels. They are highly territorial and aggressively defensive, attacking intruders far larger than themselves. Butterfly fish, angelfish, and other anemone-feeding species are harassed relentlessly, nipped and chased away long before they reach the tentacles. This behavior reduces damage to the anemone, which otherwise might lose tissue to repeated grazing. The fish do not weigh risks the way larger animals do. Their confidence comes from proximity. If danger escalates, retreat is immediate and absolute. They simply vanish into the tentacles. This aggression is constant. Clownfish spend much of their day patrolling the boundary between safe and unsafe space, responding instantly to movement near the anemone. There is no pause, no negotiation. Any unfamiliar presence is treated as a threat. This behavior shapes the local neighborhood, creating a bubble of exclusion around the anemone that extends beyond the reach of its stings. The fortress gains an outer perimeter enforced by behavior rather than venom. Social structure intensifies this defense. Clownfish live in strict hierarchies, typically centered around a dominant breeding pair. All others in the group are subordinate, smaller, and sexually immature. This hierarchy is maintained through constant low-level aggression, chasing, and posturing. There is no room for ambiguity. Rank determines access to space within the anemone, proximity to safety, and future reproductive potential. This social rigidity serves a purpose. It prevents internal conflict from destabilizing the group. Only one breeding female exists at a time, reducing competition that could distract from defense. If the dominant female dies, the largest male transitions into her role, a remarkable physiological shift that ensures continuity without migration or searching for new partners. The home remains occupied. The nursery remains protected. Reproduction itself is tightly bound to the anemone. Eggs are laid on nearby hard surfaces, usually rock or coral at the base of the tentacles. This location is not accidental. The anemone's defenses deter most egg predators, while the fish themselves provide constant care. Males fan the eggs with their fins, cleaning and oxygenating them until hatching. During this period, aggression intensifies. Intruders are met with immediate attack, regardless of size. The future of the group is literally glued to the substrate, and it is defended without hesitation. This relentless protection benefits the anemone as well. A resident clownfish group reduces the likelihood that the anemone will be overgrown by algae or damaged by persistent grazers. Waste products from the fish provide nutrients that the anemone and its symbiotic algae can use, subtly enhancing growth and recovery. The fortress does not merely shelter tenants, it becomes more productive because of them. The mutualism extends beyond individuals. Clownfish presence influences fish distribution on the reef. Smaller species cluster near anemones, using them as reference points or temporary refuges, even if they cannot enter the tentacles themselves. Predators learn to avoid these zones, rerouting hunting paths around them. Over time, the reef's spatial organization shifts, with anemones and their tenants acting as anchors in a constantly moving environment. The clownfish's physiology supports this lifestyle. Its compact body allows rapid maneuvering within tight spaces. Its coloration, bright and high contrast, serves as a signal rather than camouflage, advertising confidence and occupancy. This visibility reinforces territorial boundaries, warning other fish that this space is defended. The fish does not hide its presence. It broadcasts it. Thermal and environmental conditions further shape behavior. Clownfish are sensitive to temperature changes, which affect metabolism, aggression levels, and reproductive timing. In warmer conditions, activity increases, defense intensifies, and egg development accelerates. In cooler periods, movement slows, but territoriality remains. The anemone provides thermal stability at microscales, buffering sudden fluctuations and allowing the fish to remain active when surrounding waters shift. The relationship is not without cost. Clownfish rarely stray far from their anemone. This limits foraging range and diet diversity. They trade mobility for security, accepting a smaller world in exchange for survival. This trade-off works because the anemone's protection allows longevity and repeated breeding attempts. In ecological terms, the clownfish invests in place rather than movement. When anemones are lost, the consequences for clownfish are immediate and severe. Without the fortress, their defenses collapse. Aggression becomes meaningless without a retreat point. Social hierarchies break down as individuals scatter or fall prey. The fish do not simply relocate easily. Suitable anemones are scarce, and competition for remaining ones is intense. Many clownfish die not because food disappears, but because home does. This dependence highlights a broader truth about reef ecosystems. Survival is not determined solely by who eats whom, but by who controls safe space. The anemone provides that space through venom. The clownfish keeps it functional through behavior. Together, they form a unit stronger than either alone. There is something almost brutally simple in this arrangement. Protect the home. Protect the nursery. Protect the future. Every action the clownfish takes can be traced back to these priorities. Aggression is not cruelty. It is maintenance. Hierarchy is not oppression. It is efficiency. Constant vigilance is not paranoia. It is adaptation. Watching a clownfish launch itself at a fish many times its size, only to retreat instantly into tentacles that flash with lethal promise, reveals the logic of the system. The fish is not brave. It is positioned correctly. Its courage is borrowed from architecture it did not build but actively maintains. The anemone may be the wall, but the clownfish are the guards. They do not sleep on duty. They do not patrol in shifts. Their entire existence is oriented around keeping the fortress alive, intact, and occupied. In return, they gain a future in a reef that would otherwise be unforgiving. In a world often focused on apex predators and massive ecosystem engineers, clownfish offer a different lesson. Impact is not always a matter of size or strength. Sometimes it is persistence. Sometimes it is aggression applied endlessly at small scales. Sometimes it is knowing exactly what must be defended and never letting it go. The smallest workers can be the most relentless. The ocean does not always need destruction to change. Sometimes it only needs the possibility of it. Along the edges of reefs, where shallow structure drops into blue depth, and across seagrass flats that fade into open water, a presence moves that never settles. It does not build shelters, stack stones, or carve dens. It reshapes ecosystems simply by being unpredictable. The tiger shark does not announce itself with constant violence. It reorganizes life through pressure. From a distance, a tiger shark appears almost casual, its broad head and slow, rolling swim giving the impression of indifference. This illusion is dangerous. Its body is built not for bursts of speed, but for endurance, a cruising predator designed to cover immense distances without tiring. Muscle mass is distributed for sustained motion. A powerful tail drives it forward with economical strokes, while large pectoral fins provide lift and stability. The shark is always moving, and that movement is what gives it influence. Tiger sharks are not specialists tied to one habitat. They patrol seagrass beds, reef edges, sandy plains, and open water, crossing boundaries that many animals treat as hard limits. This mobility turns the seascape into a connected system of risk. No place remains permanently safe. The shark's arrival is often unseen, sensed only through subtle cues that prey species have evolved to recognize over millions of years. Those cues matter more than teeth. When a tiger shark begins cruising along a seagrass meadow, herbivores respond immediately. Dugongs alter feeding routes. Green turtles shorten grazing bouts or shift to shallower patches closer to refuge. Fish schools tighten, reducing foraging time in exposed zones. None of these animals need to be attacked to change behavior. The shark's mere presence transforms how energy moves through the system. This phenomenon, known as risk-mediated behavior, is one of the tiger shark's most powerful ecological effects. Predation does not need to be frequent to be influential. In fact, infrequent but unpredictable attacks generate the strongest responses. Prey species cannot habituate. They must assume that danger could arrive at any moment. As a result, feeding becomes cautious, movement becomes strategic, and habitats are used unevenly rather than continuously. Seagrass meadows illustrate this clearly. In areas where tiger sharks patrol regularly, turtles and dugongs avoid grazing too far from cover or spending long periods in open patches. This reduces overgrazing, allowing seagrass to recover and maintain structural integrity. Meadows remain productive not because herbivores are removed, but because their behavior is constrained. The shark becomes an invisible hand shaping plant growth without ever touching it. Reef drop-offs function similarly. These transition zones between shallow and deep water are rich in food, but high in risk. When tiger sharks patrol these edges, smaller predators hesitate to cross and prey species cluster closer to structure. The drop-off becomes a dynamic boundary, its ecological role shifting depending on shark activity. At times, it is a feeding corridor. At others, it is a barrier. The reef's layout gains meaning through movement rather than material. The tiger shark's physiology reinforces this role. Its sensory systems are finely tuned to detect electrical signals, pressure changes, and chemical cues over long distances. It does not need to rush. It samples the environment continuously, making decisions based on information prey animals cannot perceive. This asymmetry of awareness is central to its influence. Prey sense danger without knowing its source or direction, amplifying uncertainty. Dietary flexibility adds another layer. Tiger sharks are famously indiscriminate, consuming fish, turtles, birds, rays, and carrion. This generalist strategy allows them to exploit whatever is available, preventing prey species from predicting which behavior will reduce risk. No single adaptation provides safety. Avoidance becomes the only reliable strategy, and avoidance reshapes space. This constant pressure prevents any one species from dominating key habitats. Herbivores cannot graze without restraint. Mid-level predators cannot hunt without vigilance. Scavengers must time their activity carefully. The system remains fluid, balanced not by removal, but by hesitation. The tiger shark does not enforce order through frequent killing. It enforces it through uncertainty. The impact extends across time as well as space. Many prey species alter activity patterns, feeding at different times of day or night to reduce overlap with shark patrols. These temporal shifts ripple outward, affecting interactions between species that may never encounter the shark directly. The ecosystem reorganizes itself around the rhythm of risk. When tiger sharks disappear, these patterns unravel. Herbivores graze longer and more freely. Seagrass beds thin and fragment. Reef edges lose their role as dynamic boundaries and become overused corridors. The system does not collapse immediately. It drifts. Productivity shifts. Structure weakens. The absence of pressure creates ecological slack, and slack invites imbalance. What makes the tiger shark's role difficult to perceive is its subtlety. There are no obvious construction sites, no visible modifications. The reef looks the same at a glance. Only careful observation reveals that animals are moving differently, feeding differently, choosing differently. The builder is not changing the environment directly. It is changing decisions. This is perhaps the most primitive form of ecosystem engineering. No tools, no structures, just presence. The tiger shark shapes the seascape by forcing every other organism to answer a single question repeatedly. Is this worth the risk? The answers determine where plants grow, where animals feed, and where life concentrates. Watching a tiger shark pass along a reef edge, its striped flanks fading into blue, it is easy to underestimate the scale of its influence. It does not linger. It does not dominate visually. It moves on. But long after it has gone, its effect remains, encoded in altered behavior and redistributed energy. In this way, the tiger shark builds without building. It does not leave walls or dens or barriers. It leaves caution. And caution, applied consistently across an ecosystem, is as powerful as any physical structure. Sometimes the builder is just pressure. The ocean changes when orcas arrive. Not suddenly, not explosively, but decisively. Currents keep moving. Light still fractures across the surface. Fish continue to school and disperse. Yet beneath these familiar motions, the rules have shifted. The arrival of an orca pod rewrites the operating manual of the ecosystem, not through constant violence, but through coordination, memory, and intent. This is not a predator acting alone. This is a supervisory force. Orcas do not hunt as individuals. They hunt as units bound by lifelong social structure, shared knowledge, and cultural tradition. A pod is not just a group of animals moving together. It is a distributed intelligence, one that remembers migration routes, prey behavior, seasonal patterns, and past successes. Each member occupies a role shaped by age, experience, and specialization. Calves learn by observing. Adults refine techniques over decades. Elders, particularly post-reproductive females, carry ecological memory that extends beyond the lifespan of any single generation. This collective memory gives orcas power that no solitary predator can match. They do not simply respond to prey. They anticipate it. They know where animals will move before those animals arrive. They understand how fear propagates through prey populations and how to exploit it. When an orca pod enters an area, it is not just hunting. It is auditing the system. Consider how this plays out along coastlines and continental shelves. Seals haul out on beaches that have been safe for years, following patterns reinforced by survival. Then orcas begin patrolling nearby waters. The seals respond almost immediately. Haul-out sites empty. Travel routes change. Feeding grounds are abandoned or used only at night. The orcas may kill a few individuals, but far more significant is what they force the rest to stop doing. Energy flow shifts. Prey species reduce foraging efficiency to reduce risk. That lost energy ripples upward and outward. The effect extends beyond direct prey. Other predators take notice. Sharks alter patrol routes. Mid-level predators avoid areas where orcas operate, not because they are hunted directly in most cases, but because confrontation is unpredictable and often fatal. Even large sharks yield space. The seascape becomes partitioned not by physical barriers, but by dominance. Orcas enforce these partitions through presence and coordination. A lone predator can be avoided or outmaneuvered. A pod cannot. Orcas communicate continuously through vocalizations and body language, maintaining cohesion over distances that would fragment other groups. They surround prey. They drive it. They corral it into disadvantageous terrain. They use the environment as part of the hunt, exploiting shorelines, ice edges, and bathymetric features with practiced precision. This coordination produces cascading effects across food webs. When seals abandon certain feeding grounds, fish populations rebound in those areas. When sharks avoid reef edges patrolled by orcas, mesopredator behavior changes, altering pressure on smaller prey. The system reorganizes itself around the pod's movement, redistributing biomass without requiring constant consumption. The orca's diet flexibility amplifies this influence. Different populations specialize in different prey, from fish to marine mammals to sharks. These specializations are cultural, passed down through learning rather than genetics. As a result, the same species can function as entirely different ecological forces depending on where and how it hunts. In one region, orcas regulate fish populations. In another, they suppress apex predators like sharks. In each case, the outcome is a reshaped ecosystem driven by learned behavior. Physiology supports this role. Orcas maintain high body temperatures in cold water through thick blubber and efficient circulation, allowing them to operate across vast thermal gradients. Their stamina is exceptional. They can patrol territories for hours or days, maintaining pressure without exhausting themselves. This endurance matters more than speed. It allows orcas to be persistent, to outlast avoidance strategies, to enforce boundaries over time, rather than through single encounters. Their sensory world is equally important. Echolocation provides detailed information about prey location, movement, and even internal structure. This allows orcas to make informed decisions about whether to pursue, how to pursue, and when to disengage. They are not guessing. They are selecting. The intelligence behind this selection is not abstract. It is practical. Orcas do not waste energy on low-reward pursuits. They do not chase prey into terrain that favors escape unless there is strategic advantage. They adapt techniques when conditions change. This adaptability makes them stabilizing forces as much as disruptive ones. They prevent any single prey species from becoming too dominant, but they also avoid destabilizing systems through overexploitation. When orcas remove large sharks from an area, the consequences are complex. In some systems, shark suppression allows herbivores to expand, increasing grazing pressure. In others, it alters mesopredator dynamics, relieving pressure on smaller fish. These outcomes vary by context, but the common factor is that orcas initiate change at the top, and that change propagates downward. What distinguishes orcas from other apex predators is intentionality layered over instinct. They do not merely react. They plan. They coordinate. They teach. The environment becomes something they manage rather than endure. This management does not resemble human governance, but it achieves similar outcomes. redistribution of resources, enforcement of boundaries, maintenance of balance through oversight rather than constant force. When orcas disappear, these supervisory effects vanish. Systems do not collapse immediately. Instead, they drift into new configurations, often less stable. Prey species resume unchecked behavior. Other predators expand into vacated roles. Energy flows differently. The absence of oversight creates ecological noise, a proliferation of uncoordinated pressures rather than a single regulating influence. Reintroducing orcas to such systems does not instantly restore order. It takes time for prey to relearn risk, for other predators to adjust, for patterns to re-establish. But when it happens, the transformation is unmistakable. Movement becomes structured again. Habitats regain their strategic value. The ecosystem starts making sense. Watching an orca pod move through open water reveals none of this complexity at first glance. Their black and white bodies cut clean lines through the sea. They surface, breathe, submerge, repeat. There is no visible sign of control. Yet every animal within range is adjusting behavior, often without conscious awareness, responding to cues shaped by evolutionary memory. This is the final lesson of ecosystem engineering. Not all builders manipulate matter. Some manipulate choice. By changing what is safe, what is risky, what is profitable and what is not, they reshape the entire system without leaving physical traces. Orcas do not build reefs. They do not graze meadows. They do not dig burrows or stack stones. They decide who gets to use those things, when, and for how long. They are editors, not authors. Supervisors, not laborers. Intelligence plus coordination creates effects that scale beyond the individual. It creates order without walls, structure without permanence, control without constant enforcement. The ocean looks wild because its management is invisible. The ocean is not wild. It is managed.